Hi, Chandler. Okay, I think these first ones are harder than some of the later ones we did, so we want to try to get through these, and on the test, do the best you can on these, and then do well on the second part. But I want to draw you some pictures, and maybe some pictures will help. So this is how maybe you can try to think, okay, what do I have to do? What do I multiply on all of these? So you'll see. So a man has 6 shirts and 4 ties. Assume they all match. How many different combinations are there? Okay, 6 shirts and 4 ties. Let's just say the shirts are shirt A, B, C, D, and E, F. So you can kind of try to draw it. And then maybe the ties are W, X, Y, and Z, like that. Okay, so they can all match. So if I try to draw some kind of a picture, I can take shirt A with W, A with Y, A with X, or doesn't matter, X, Y, and A with Z. That's shirt A with all the ties. Then shirt B could go with all the ties. And then shirt C can go with all of the ties. And shirt D, E, and F. Okay, so there's all the combinations. A with all of them, B with all of them. So see how that's 4 this way and 6 this way? So there's got to be 24 total combinations in there. So there's a picture of why that one is 24. That's the answer to that one, 24. So I just tried to draw it. So if it's an easy draw, go ahead and just draw it, and then that's the reason that instead of trying to memorize, oh, that's always multiplication, sometimes it's hard to decide what to do. So sometimes a drawing helps. Okay, so a person must travel to 8 cities to promote a new campaign. How many different trips are there if all of the possible things are the same? Okay, let's say these are the cities. 1, 2, 3, 4, 5, 6, 7, 8. Okay, he could go like this, just around the horn like that. That would be one way to do it. Or he could go this one first, and then that one, and then that one, and that one, that one, that one, that one. And then he could go this one, and then that one, and that one, and that one, and that one. So there's all kinds of, there's lots and lots and lots of possibilities starting at this city. Okay, so if we do all the combinations from that city, then there's 7 left. Okay, so from 7, because see, really going this way and this way, going around the horn is another way to do it. There's 7 of these, and then there's some more this way, and so all of these different combinations, that's the 7th one. Then this one can go all different combinations if we start there. And this one can go all different combinations and start there. Okay, when you have all of this stuff that can do any different kind of way, it's how many you have times the next city, how many are left, times the next city, how many are left, times the next city, how many are left, times the next one, times the next one, times the next one, times the next one. That's what 8 factorial is. There's a button on your calculator that will do that. And factorial is sometimes hard to understand. So if you just do 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, it's 40,000. There's 40,000 different ways you can go around 8 cities. See the math key right here? If you say math and go over to probability, that's what that symbol is right there. So if I type in 8 math probability, it's called factorial. It's like 8. It's still 40,320. Now showing you where the button is the easy part. When to use it is the hard part. So if there's a question exactly like this, it's just factorial. How many different paths are there? If you have 8 different things, how many pathways are there? That's just factorial. Okay, like I say, these first ones are pretty confusing, so don't get too discouraged. Try to draw a picture. If you can't draw a picture, try to mess with factorial a little bit. Okay, number 3. Hopefully these will be multiple choice at least. Okay, companies on the list of New York Stock Exchange can either have 1 letter, 2 letters, or 3 letters, and repetitions are allowed. What's the maximum number of companies? Okay, let's see if we can draw this one, the 1 letters. Okay, we can have A. A company could be called A. There is a company called A. It's AT&T. A company could be called B, a company could be called C, all the way up to a company could be called Z. So here's the single letter, people. There's 26 possibilities. Okay, what about two letters? So it could be AA, AB, AC, AD, all the way up to AZ. But then it could be BA, BB, BC, BD, all the way up to BZ, all the way down to ZA, and then ZB, and ZC, all the way up to ZZ. So this is 26 that way by 26 that way, so it's 26 by 26. So whatever that one is, that's how many there are for that. We could do that. 26 times 26 is 676. So there's 26 singles, there's 676 doubles, and now we got to see the three letters. Okay, it could be AAA, AAB, AAC, all the way to AAZ. So there's 26 like that. Okay, see, that's all we did was change the first one. Okay, what if I changed the second one? It could be ABA, ACA, ADA, ABCDEA, and so on. And actually, I should have gone, okay, let me try that again. I'm only changing the B. ABA, AB, B, ABC, ABD, ABE. So AB is what's in common for all of these. So that's the ABs. Then it could do AC, and then AC, and then AC. So that's the row of ACs for 26. And AD, and AD. So the ADs go across 26, and then the AEs, 26. So I have 26 that way, 26 that way. So I did all the AAs, I did all the ABs, we did all the ACs, all the ADs, all the ADs. So far it's 26 by 26, but these all started with A. What if I started them all with B? So it would be BAB, and then BAC, and BA, so the BAs can start. There'll be 26 more of those. So it's like 26 by 26 by 26. Okay, so see, when there was 26 possibilities once, it was 26 to the 1 power. When there was 26 possibilities twice, it was 26 to the 2 power. And now with there's 26 letters 3 times, it's 26 to the 3 power. So 26 to the first, so the singles had 26, the doubles had 26 squared, and now the triples are going to have 26 to the third, which is 17,576. So there's 17,576 of these. So we have 26 singles, 676 doubles, and 17,000 triples. So 17,576 plus 600 plus 676 plus 26 is 18,278, which is what their answer is right there. Okay. So a local network requires 8 letters for users' names. How many users, so the lower and uppercase are the same. How many user names are possible for a local area network? 1, 2, 3, 4, 5, 6, 7, 8. It's kind of like this one up here. We have 8 cities. So if we would have said you had to start in city A and go to 8 different cities, was 8 of these, 8 of these. It's the same basic thing. What if we could have any letter here and then anything there, any other letter, anything there, any other letter, anything there. But see, up here we only had 8 possible starters, so it was 8. Let's see here, that's not right. Let's start over. Let me start over that explanation. We're dealing with the alphabet here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, it could be A. Okay. It could be A, B. And A, B, C. And so on. So the A, so that's 26 that way, 26 that way. Because this one could change. So, oops, not 26 that way. 1, 2, 3, 4, 5, 6, 7, 8 this way, and 26 that way. Sorry. So starting with all A's, we could have 8 this way, 26 that way. Okay, what if we started with all letter B's? Could it B, 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 A, B, 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 C, B, 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 C, and so on. So there would be 8 that way and 26 that way. Oh, this might be too hard to draw. We have 26 letters, and we get to pick 8 of them. Okay, well, it's 26 to the 8th power. I'm not sure how to draw that. If we have 26 possibilities, and they can be in 8 different spots, it's just 26 to the 8th power. It's that giant number. When it's that giant number, they usually just answer 26 to the 8th power, which is what she's got right there, 26 to the 8th power. Like I say, some of these that one's a really hard one to draw. So forget about the drawing on that one. Hopefully that would be a multiple choice. It's a lot. 8 letters, 26 letters, 8 different ways. Just pick a really big number. Okay. Once we get through this first page, it's going to get a little bit easier. Suppose we have 40 cars. How many cars can the top 3 be? So we have 1, 2, 3. We want the first 3 finishes. Okay, so there's 40 cars, so it could be car 1, 2, 3. That could be the top 3. Or it could be the top. It could be car 35, and could be car 7, and then it could be car 2. See what they're saying? So what they want, it doesn't. But this, it couldn't be this 1, 1, 1. See, that's no such thing. Car 1, car 1, car 1 can't be repeated like that. Okay, so when the order and then it could be car 3, car 2, car 1. See, that's different than this one, because this is first place, second place, third place, first place, second place. Those are different things. So when the order like that doesn't matter, it's called a permutation. What we have is we have 40 cars, and we want, how can 3 of them be ordered? Okay, it goes in your calculator like that. 40 cars permeate 3. Permutations are when this can't happen, and when order doesn't matter. Those are different things. So 40 permutations of 3. Here's where that is on your calculator. You don't even have to remember all that factorial stuff. If you can figure out if it's a permutation, you go 40, and then you go to math, the math key right there, back over to probability. That stands for permutation. See, the N means you put the total number first, and then how many cars you can have second. So that means 40 permutations of 3. You can have 3 winners out of 40 cars. It's 59,280. That's where she got that number. 40 total cars, 3 top 3 in order. See, permutation means order matters. This one and this one count as 2 different orders. Okay. 4 members of a 20-person committee are to be selected randomly to serve as chair, vice chair. So let's just call this like first place, second place, third place, fourth place. See, it's almost the same. You have 20 people, they can get first, second, third, or fourth place. The first person selected, second person, okay. How many different leadership structures are available? Okay, so see, let's say the first person's name's A, the second person's name is B, the third person's name is C, and then the fourth person's name is D. Of course, there are 20 people, so we have A, B, C, D, E, F, G. Okay, let's say these are the 4 people that get elected. President, Vice President, Secretary, Treasurer. See, this is different. Same 4 people, but they're different order. So this is one and this is another. That means permutation. I don't know how to spell it. Permutation. There's 20 people. We would like to order 4. How many different orders of 4 are there? So we go 20, math, permutation of 4. That's 4 winners out of 20. There's 116,280 of those different combinations. So if first, second, third, fourth place, if the order matters, it's called a permutation. Okay, let's see. Number 7. I'm not sure I remember how to get number 7. I think 7 is a hard one. We have 3 A's, 2 C's, 2 G's, and some T's. So that's 10 spots. A, C, C, G, G, T, T, T. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, if you have any kind of letters in 10 spots, that would just be 10 factorial. That's 10 times 9 times 8 times 7 times 6. Kind of look up here. We had 8 cities in whatever order. Here we have 10 spots in whatever order. But since there's 3 A's, see, moving these 2 A's around, if this would have been A, B, C, D, E, F, G, H, I, J, K, moving these 2 positions around would have made it different. It would have made it B, A. But moving those 2 spots around, see, it still is A, C, C, G, G, T, T, T. So those, moving the A's around don't matter. So we have to divide out how many A's there are. So we're going to divide out 3 super combinations. But the same thing is with the C's. We have to divide out 2 C combinations. And the same thing with the G's. If we switch the G's, we have to divide out 2 combinations. And then the same thing with the T's. We have to divide out 3 combinations. So we have 10 total, but 3 are repeats, 2 are repeats, 2 are repeats, and 3 are repeats. The way we put that in our calculator, see, that really means 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, divided by 3 times 2 times 1, that's this, divided by 2 times 1, divided by 2 times 1, divided by 3 times 2 times 1. Okay, but since we have that button on our calculator, we have 10, remember it's under math probability, and it's the 4th one down. There's the 10 factorial. Okay, let's divide it by 3 factorial. So divided by 3 math factorial. And then divide it by this one. So don't hit enter yet. Just keep dividing by 2 math factorial. Probability factorial. And then divide it by this 2 factorial, so divided by another 2 math probability factorial. And then divide it by this one, 3 factorial, so divided by another 3. So see, we have 10 divided by 3, divided by 2, divided by 2, divided by 3 is 25,200, which is what they have right there. Okay, after that it's going to get easier. So sometimes it's just hard to figure out all this factorial stuff. You know, you can watch the 1 through 7 again if I went too fast. Okay, the grade level appeals process at a university requires that a jury can be structured using 5, so they want 5 people selected from a pool of 8 students and 10 faculty. So here's the pool. There's 18 people in the pool. What's the probability the selected jury are all students? So they want 5 people selected out of 18. So 1, 2, 3, 4, 5. There's the jury. Okay, but they want it to be, what's the probability of all students? So the first one selected is a student, 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 student. So I'm trying to draw what they want. They want student, 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 student. Okay, let's say we pull out, we have a bag of 18. We have 8 out of 18 chance that this person is a student. Okay, assume we got that student. That means there's only 7 students left, and there's only 17 people left in the bag. Assume we got that student. Means there's only 6 left out of 16. Assume we have that one. Means there's only 5 left out of 15. Assume we got that one. That means there's only 4 left out of 14. That's the answer. 8 18ths times 7 17ths times 6 16ths. So it all has to happen. This one, then this one, then this one, then this one, then this one. We need 5 things to happen in a row. You multiply them all together. So here's how you can do that. You don't have to do all the fractions. Multiplication and division can come in any order. So I'm just going to say 8 times 7 times 6 times 5 times 4. 8, 7, 6, 5, 4. But don't even hit enter. Then divide by 18, divide by 17, divide by 16, divide by 15, divide by 14. Now look at what their answer is. 1 out of 153. We got 0.0065. We'll turn it into a fraction with this math button. Hit math, and then it's the very first thing. See fraction? It'll take your answer, turn it into a fraction, 1 out of 153. Now probably she taught you how to do this with factorials, but I think this is much easier to draw and then just figure out each one and put it all together. Let's try part B of that one. What's the probability that it was all, what's the probability that it was all faculty? Okay, so they still want 5. 1, 2, 3, 4, 5. But now they want the first one to be a faculty, 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 faculty. So in this bag, remember there were students and faculty. Okay, there were 8 students and 10 faculty. So the odds of picking out a faculty were 10 out of 18. Assume we get it, so there's only 9 left out of 17. Assume we get it, there's only 8 left out of 16. Assume you get it, there's 7 out of 15. Assume you get it, it's 6 out of 14. So it's the same idea, only the probabilities change. So it's 10, 9, 8, 7, 6 divided by all of those. So it's 10 times 9 times 8 times 7 times 6 divided by 18 divided by 17 divided by 16 divided by 15 divided by 14. 0.029. If I hit the math key, say fraction, it's 1 out of 34, which is what they have. Okay, what's the probability of 2 students and 3 faculty? So student, student, faculty, faculty, faculty. Okay, it could be like this, but just notice it could also be student, faculty, student, faculty, faculty. See that this is also 2 students and 3 faculties, but the extra student could be there. The extra student could be there. We have to figure out how many combinations there are. Okay, so this is called a combination. The other one, these were different people. It was like first place and third place. They're just both students. So now there's not a special combination. A combination, what I want to know is how many times can 2 students fit out of 5? So I have 5 spots and I would like the combos of 2. Where can 2 people be moved around in 5 spots? Okay, your calculator will tell you that also. Okay, so say 5, that's this number. Math, probability, see that's what the C is. That stands for combos. So this means out of 5, what are the combos of 2? That means this could happen 10 times. Student, student, see the 2 students could be split apart wherever 10 different ways. Because it could have been faculty, student, student, faculty, faculty. See, all by moving the S's around, there's 10 different ways to do that. So there's 5 spots we want to move around 2 students. It's 10 times. So whatever we get out of this, it could happen again and again and again. I'll show you in just a second what I mean by that. So just know that there's 10 combinations. Let's get this one. What if the very first one was a student? That would be 8 out of 18. The next one, assume we get a student, then we have 7 students left out of 17. But now we need faculty. See, there's still 10 faculty in there, so there's 10 faculty out of only 16 people left. Assume we get it. Now there's only 9 faculty out of 15 people in the bag. Assume we get it. Now there's only 8 faculty out of 14 people in the bag. So student, SSFFF is this number. 9, 7, 10, 9, 8. Oops. 8, 7, 10, 9, 8. And then divide by 18, 17, 16, 15, 14. I'm going to math fraction that. It's 2 out of 51. So this specific one is 2 out of 51. Okay, that's in this exact order. Student, student, faculty, faculty, faculty. That's 2 out of 51 chances. What if we mix it up a little bit? See, what if we were doing just this one? Okay, that one would still be 8 out of 18. 8 students out of 18. Then if we wanted a faculty, okay, there's still 10 in there, but out of only 17. Then we want a student. Well, we already have a student, so there's only 7 left out of 16. Then we want a faculty. Well, we got one over here, so there's only 9 left out of 15. And then we want another faculty, 8 out of 14. Okay, see how the top numbers are the same? I got 8, 7, 10, 9, 8, just like I had 8, 7, 10, 9, 8. And then the bottom numbers are also exactly the same. So when we put it all in our calculator, that's going to be 2 out of 51. And then this order right here, SFF, that's going to be 2 out of 51. And this one's going to be 2. They're all 2 out of 51. So we really only had to find the first one. It's 2 out of 51, but we do have to know there's 10 of them. So it's 2 out of 51 10 times. So 2 out of 51 times 10 is 20 out of 51, which is what they have there. See, up here we didn't have to get the combinations because there's only one way to get FFFFF. You can move those around and it's still the same. Okay, number 9. In 2013, there were 32,719 traffic deaths in the U.S. Of these, 10,000 were alcohol related. So we have 10,000 alcohol out of 32,000 total. Okay, what's the probability that a random was alcohol related? So alcohol out of total. So it's just going to be 10,000, how many of these there were, out of how many total there were. So 10,000 out of 32,000, 10,076 out of 32,719 is 0379, which is what they have. 038, 30.8%. Okay, so that's where that number comes from. How many alcohol out of how many total? What's the probability they were not alcohol related? Okay, if 10,000 are alcohol, I'm just going to subtract them to get not alcohol. So 32,719 minus 10,076. So not alcohol are 22,643. So what's the probability of that? 22,643 divided by 32,719. So 22,643 divided by 32,719 is 0.692. 69%, 69.2%. Okay, that would have been one way to do it. Another way to do it is, remember, 100% is the same thing as 1. So if This is how many are alcohol. 1 minus this would be how many are not alcohol. 1 minus 0.308, see how that's the same answer? That would be another way. Everybody minus alcohol is non-alcohol. Okay, now we need 2 alcohol. So death, death, just like faculty, faculty. So I'm going to draw that. We need alcohol, alcohol. Okay, well the chances of one person being alcohol was right up here, 0.308, so that's 0.308, and then another 0.308. So it's anytime you need 2 things to happen, you multiply them together. The first one times the second one, so 308 times 308. .09095, which is what they have right there. Okay, what's the probability that neither were alcohol? So I'm going to draw those two. Not. Okay, well we found that up here already. The nots were 0.692. So not alcohol was 692. And not alcohol was 692. So 692 times 692 is 479, which is what they have. Okay, at least one. Okay, there's 2 ways to do at least one. At least one is always 1 minus not. 1 minus no. So you can remember that formula. It's everybody minus no. At least one is 1 minus no. Well, we just did no. That's 0.479. So we could just do 1 minus 0.479. Okay, so 1 minus 0.479 is 521. That's where that one's coming from. That would be one way to remember. Or if you forget that, you can just add them all up. So at least one. So that would be alcohol, alcohol. That's at least one because that's both of them. We already know what that answer was. We did it up here. Alcohol, alcohol was 0.95. Okay, we could do alcohol, not alcohol. So we would have to figure out what that one is. Okay, alcohol was 308, and not alcohol was, what was not alcohol? 692. Okay, 308 times 692. 213. But it could have been one other order. See, it could have also been not alcohol, alcohol. So that would have been 692, and this one would have been 308. So that's another 213. So see how this is at least one? We have 9%, another 21%, and another 21%. We got to add them all up. So 0.095 plus 0.213 plus another 0.213. There's the same answer, 521. So the only thing that was missing, the reason at least one is always there, there's one more choice, not, and that's the one that doesn't count. So not doesn't count. So we could have done everybody minus not. That's what that formula comes from. So I just like to remember that. At least one is 1 minus no. Okay, suppose E is 37 and F is 22. Find E or F if E and F are mutually exclusive. Okay, remember OR. OR is E plus F minus EF. It's always the first one plus the second one minus the combo. Okay, so E they gave us 0.37. F they gave us 0.22. Mutually exclusive means they never happen together. So that means they never happen together. So it's just 37 plus 22. That's where 59 is coming from. Okay, E and F, and that's E and F, that's both of them. E, which is 37, times F, which is 22. See, and means they both have to happen. It's just like up here. When two things have to happen, you multiply them. When two things have to happen, you multiply them. Okay, so 0.37 times 0.22 is where they got 0814. Okay, so here we go. Let's remember this thing. That formula is F and E divided by E. Okay, it's the and of those divided by just the E. Okay, so let's put some of this together here, because the very first thing what they want to know is the and, which is that. Okay, so the whole formula is 0.7. It equals E and F, which we don't know yet. That's what they're asking for. Divided by E, which they gave us, which is right here, 0.15. See, they also gave us F, but F's not in the problem anywhere. This number is always the combo, E and F. Now, I know up here we did the combo. When we did the and, we just multiplied them together, but it said they were independent. If it's independent, you can just multiply it together. See, here it did not say that, so we can't assume those were just multiplied together. Okay, but we can use the formula to find E and F. So EF times 1 is just EF. So that's the and, what they want, equals 0.7 times 0.15. 0.105, which is where they're getting that from. So see, we had to use the form. First of all, we had to know the formula. The probability of E assuming, the probability of F assuming E, it's always F and E divided by the second one. If they say it's independent, if they say those are independent, you can just times them together. But if they don't say that, you cannot just times them together. That's why we could just multiply these together, because they said they were independent to get that and. Okay, E or F. Okay, E or F. Or it's the probability of E plus the probability of F minus E or E and F. Okay, so or is the first one plus the second one minus the combo. Well, we know the combo now. That's how come they had us find it. So E is 15. F is 45. EF was 0.105. Okay, so 0.15 plus 0.45 minus 0.105. 0.495, which is where they're getting that number from. Okay, see how these two are different? The letters are a different order. Okay, so here's C. They want E assuming F. See up here, we divided by E. You always divide by the second one. So this is going to be E and F divided by F. Okay, well, we found E and F. That was 105, and now we're going to divide it by the F number, which is 45. So 105 divided by 45. 233, which is where they got that number. Are E and F independent? Okay, see how we used the formula to figure out that E and F over here. We found out that E and F was 105. Okay, if we just multiply together E and F, E times F, so 0.15 times 0.45 is 0.0675. See, if the multiplication is the same number as the formula, then they're independent. That's what independent means. It means it doesn't matter how you do it. But they're not. When we multiply them, it's 0.06. When we did the formula, it was 0.10. So no, they are not the same. That means it's not independent. All right, so here we got a table. Following table, okay, verify its probability model. Okay, so all probabilities are less than or equal to 1, so that's checked. They have to be under 1. Actually, we should say greater than 0. I'll probably write it like this: 0 probability of the event, like that, between 0 and 1. So yes, they all are. That's one criteria. The other criteria has to add up to 100%. So 0.25 plus 0.19 plus 0.13 plus 0.11 plus 0.09 plus 0.23. So yes, part 2, the probability of the events equal the sum, I'll put, that stands for sum, is equal to 1. The sum of the probability of the events is equal to 1. Okay, if a Girl Scout is selling cookies to people who are in our shopping mall, what's the probability that the next box sold will be peanut butter or peanut butter patties or peanut butter sandwiches? Okay, so remember again, or. We need peanut butter patty, the probability of patties, plus the probability of sandwiches, minus the probability of patties and sandwiches. But you can't have patties and sandwiches, so that's just going to be 0. So peanut butter patties is 0.13. Peanut butter sandwiches is 0.11. 13 plus 11 is 24, which is what they have. Okay, if a Girl Scout is selling cookies to people who randomly enter a mall, what is the probability the next box sold will be Thin Mints, Samoyas, or shortbreads? So the probability of thin, the probability of Samoya, the probability of short, minus the probability of thin times short times, but again, they can't be all three, so that's just going to be 0. So or is always yes plus yes plus yes minus the multipliers. So there we go. So thin is 25 plus the Samoyas is 19 plus the shortbread is 09. So 25 plus 19 plus 09 is 53, which is what they have right there. Okay, what's the probability the next box will not be a Thin Mint? Okay, well, if a Thin Mint is 25, not Thin Mint must be 75. You could add them all up, but if this is yes, the rest of it is no. So the probability of a Thin Mint, that's all they want, is 75. That's where that comes from. All right, so hopefully there's some like that. The following represent the results of a survey. Individuals are asked as low with this is the ideal number of children. So 5 said 0, 2 said 1, 87 said 2, and so on. So here's the females, here's the males, and here's the total. What's the probability an individual, so that means male or female, believes the ideal number is 2? So here's individuals. So it's 155 out of 297. 155 out of 297. 522, which is what they have. Okay, what's the probability an individual is female? So now it has to be only women and believes the idea. What's the probability an individual is female and believes the ideal number is children. So, okay, here's female, 87 out of 297. So 87 female out of 297. So she has to be a female and believes. So 87 out of the total is 293. 293. Okay, what's the probability a random individual who took this survey is female or believes the ideal number of children is 2? Okay, remember or again? Okay, that's the probability of female plus the probability of 2, the ideal number is 2, minus the probability of female and 2. Okay, so what's the probability someone is just female? Okay, that's 188. See, there's 188. So see, that's just female. That's 188 out of 297. What's the probability that people thought it was 2? See, people that thought it was 2 was 155. So we got females are 188. People who liked 2 was 155 out of 297. But then we have to subtract female and 2. See, female and 2 is this one right here. 87 people were both female and 2. So female and 2 was 87 out of 297. Okay, so we got 188 out of 297 plus 155 out of 297 minus 87 out of 297. 0.862. 862. Among the females, so now we're only looking at females. So now we're going to divide by 188 because that's the total. So only in the females, what's the probability the individual believes the ideal amount of children is 2? So we're only looking at females. So out of females, 87 out of 188. So 87 out of 188 females think that. 463. Okay, now, if an individual who believes the ideal number is 4, what's the probability that person is a male? Okay, so this time, we're only looking at the 4s. Now we're only looking here. That's out of 36. So out of these 36, what's the probability it was a male? It was those 8 out of 36. So the first phrase usually tells you what the divider is. See, here's what's the probability of individuals. That was 297. What's the probability of an individual? That was 297. What's the probability who took is female or? Okay, the word or has a little formula to it. And then out of only the females, so that made it 188, and now it's out of only the 4s. That's the 36. So 8 out of 36 is 222, which is what they have. Okay. A Senate committee has 29 members, and a subcommittee is to be formed by selecting 5 of the members. So we want 1, 2, 3, 4, 5. How many different committees could be formed? So we have 29 members. We have person A, person B, person C, person up to Z. That's 26. Person little a, person little b, person little c. 26, 27, 28, 29. There's our 29 members. We want 5 of them. We want any 5 of those 26. So see it's how many combinations do we want? How many members could there be? See, there's no such thing as A, because A doesn't exist 5 times. So it could be A, B, C, D, E. So we want 5 different ways out of 29. So we have 29 and we would like to choose 5. Now we're picking choose. Remember permutations, here's the difference, 5 permutations of 5. That means A, B, C, D, E. is different than A, C, B, E, D. See, it's the same 5 people, but this is like order. First place, second place, third place, fourth place, fifth place. Well, they don't care what place they're in. It doesn't say president, vice president. They just want 5 people. These 5 people, these 5 people. So an order doesn't matter. It's a combo. So 29 math probability combinations of 5 is 118,755 different combinations, which is what they said, 29 combos of 5. That's what that means. Okay, state whether the random variables are discrete or continuous. You know, continuous means it's smooth. You can go from 1 to 2 with 1.1 and 1.2. There's all the numbers in between. Discrete means you got to jump from 1 and then to 2 and then to 3, and there's nothing in between. You can't have in between values. So the time it takes a light bulb to burn out, well, that's got to be continuous. It could be any amount of time. It could be 1 hour, it could be 1.1 hours, it could be 1.11 hours, so that's continuous. The number of free throw attempts before the first shot is made, see, you can't have 1.5 free throw attempts, so either 1 or 2 or 3 or 4, that's got to be discrete. The weight of a T-bone, okay, that could be 1, 1.1, 1.11, that's continuous. In a random sample of 20, the number with type A blood, you're going to have 1 person or 2 people or 3 people or 4 people, that's discrete. Okay, in 2004, Ichiro set a world record for the most hits in a season with a total of 200. So here's the total. In the following probability, the random variable X represents the number of hits he obtained in a game. So he got 0 hits 16% of the time. He got 1 hit 33% of the time, 2 hits 28%, and so on. Verify this is a discrete probability. Okay, step 1, yes. The probability of the event is always between 0 and 1. They're all between 0 and 1. It could be 0 and it could be 1. And then 2, the sum of all of the events have to equal 1. That's the Greek letter S, the sum. You could just say the sum or adds up. So we should add it up and make sure. 0.1677 plus 0.3354 plus 0.2857 plus 0.1491 plus 0.0373 plus 0.0248. All adds up to 1, so check. So yes. Draw a graph of the probability distribution. Okay. So let's say these are the zeros, these are the ones, these are the twos, these are the threes, these are the 4 hits, and these are the 5 hits. So the highest it goes up is 0.33. So how about we call this count by 5. So how about 0.5, 0.10, 0.15, 0.20, 25, 0.30, 0.35. So 0 hits goes up to 16. 1 hit goes up to 33. 2 hits goes up to 28. 3 hits goes up to 14-ish. 4 hits up to 3. And 2. Something like that. So there's the graph of the probability. Describe its shape. Okay, if we did this little smooth here, kind of smooth that out. If I ski, which is skew, I'm skiing towards to the right. It's right skewed. Unimodal means it has 1 peak. Okay, compute and interpret the mean. Okay, the mean is the average. Let's take this one up here. Okay, we have 0, so the average is like the weighted average. We have 0 times 0.1677. Then we have 1 times 0.3354. We have 2 hits at 0.2857. We have 3 hits at 0.1491. We have 4 hits at 0.0373. We have 5 hits at 0.248. It's the addition of all that. Okay, you can just type it all in at once. 0 times 0.1677, but that's just 0, so you didn't really have to put that one. Plus 1 times 0.3354. Plus 2 times 0.2857. Plus 3 times 0.1491. Plus 4 times 0.0373. Plus 5 times 0.0248. 1.6273. Which is the answer to C, 1.6. Compute the standard deviation of that variable. I can't see. How do we do standard deviation again? I got to remember what the standard deviation was. I think it was the square root of okay, I can't remember the formula, but remember we have a button that will do it. We'll put these in list 1 and these in list 2. Okay, no, these are the probabilities and this is how many. If we go to edit and put those in a list. Okay, we got to put the percentages in the first list. 1677, 3354, 2857, 1491, 0373, and 0248. And then in the next list, let's go 0, 1, 2, 3, 4, 5. No, I did it backwards. The first list is how many times in the second. Okay, we got 0, 1, 2, 3, 4, 5. Sorry. So we got 0 hits this many times. 1, 6, 7, 7. We got 1 hit this many times. 3, 3, 5, 4. We got 2 hits this many times, 2, 8, 5, 7. We got this many hits 1491 times. We got 4 hits 0373 times. And we got 5 hits 0248 times. Okay? How much it's worth, how often you got it. Okay. Stat, calculate one variable stats. You don't have to do this part on yours. List 1, comma, list 2 is what you would say. Okay. Let's see. It should give us the average here, does it? Oh yeah, see, there's the average. We figured it out the long way, but there's the average. 1.627, just like what we had, 1.627. And here's the standard deviation, right? That one didn't show up, so we'll use that one. The standard deviation is 1.1785, which is what they have, 1.2. We have 1.1785. They have it at 1.2. So we kind of cheated because I forgot the formula. Maybe you remember the formula. Okay, what's the probability that in a randomly selected game each hero got 2 hits? Well, that's this right here. What's the chances he got 2 hits? 2.857. What's the probability that a randomly selected game each got more than 1 hit? Okay, more than 1, so 1 doesn't count. So more than 1 is this many. 2 is more than 1, more than 1, more than 1, more than 1. So it doesn't say 1 or more, it says more than 1. So that's 2 plus 3 plus 4 plus 5 plus 6. So 2 is 2857 plus 3 is 1491. 4 is 0373. And 5 is 0248. 4969. Okay, in a game of roulette, a player can place a $5 bet on the number 17 and have it win 1 out of 38 times. If the metal ball lands on 17, the player wins this much. So if it lands on 17, you get this much and you have this much chance. Otherwise, the casino takes the $5. What is the expected value? Okay, so expected value is how much you win times the percent of winning plus how much you lose times the percent of losing. But of course, if you lose, it will be minus how much you lose. Okay, so we will win $175 1 out of 38 times. We will lose $5 because that's how much the bet was. Well, if we only win 1 out of 38 times, we lose 37 out of 38 times. Okay, so it's 175 times the win minus the 5 times the percentage of losses. So 175 times 1 out of 38, like that, minus 5 times 37 out of 38, like that. So we're losing 26 cents, which is what they have. So every hand you play, on average, the casino wins 26 cents. This 26 cents pays off the winners and still has some left over. That's what that means. So if you played 1,000 times, how much would you expect to lose? Well, multiply that by 1,000 and you would lose $260. A life insurance company sells $250,000 term life insurance to a 20-year-old female for $200. The probability that the female survives 1 year, okay, so if she survives, they don't have to pay. If she gets dead, they have to pay $250,000. Compute and interpret the expected value. So expected value is win times the percentage minus lose times the percentage. Okay, so let's think about what win means here. Depends on what you mean by win. Let's say staying alive is win. Okay, so if she stays alive, this is their chance of staying alive. So if she stays alive, they do not pay. So if she stays alive, she loses her $200. So she's going to lose $200 if she stays alive. She's going to win $250,000 if she gets dead. Okay, well, if this is alive, 1 minus that is get dead. So 1 minus 999,544. Is, okay, so the calculator says move the decimal 4 places. So it says 4.56 times e to the negative 4. So 1, 2, 3, 4. That's 3 zeros in that. So the probability of dead is 0.000456. So if she's dead, she's going to win $250,000. 0.000456. That's how life insurance works. They don't pay it very often, but when they pay it, they pay a lot. So this $200 will end up paying for all of that, and the insurance company will come out ahead. $250,000 times 0.000456 minus $200 if you stay alive at 999,544. So negative 85.91. Okay, that's how much you lose by paying the $200. So the insurance company makes $85 for $86, they say, for every policy. So the insurance company makes 86 for every policy sold. That's how insurance companies make money. This $200 everybody pays them easily pays off the one big loser when somebody gets dead. Okay, 19. Do the following probably represent binomial experiments? So binomial, there's some issues we have to have. The percentages are the same always. We know how many times it's going to happen. We know the n, and they have to be independent. That means one cannot affect the other. Okay, we have 15 college seniors, and they're asked their age. Okay, well, I would say no. We do know n, that's 15. And they're asked their age. Okay, they don't all have the same percentage. That age and percentage don't have anything to do with each other. So it's no because they don't all have the same probability of happening. Binomial means, remember, bi means it only has two choices. Yes, it happens, or no, it doesn't happen. See, asking their age, there's way more than two possibilities. Okay, 30 cars. We know n. A random set of 30 cars is used to obtain their mileage record. Well, same thing. That's not yes or no. Some are going to be like 100,000. Some are going to be a whole bunch of thousands. We don't know. They do not have this. It's not binomial. It's not yes and no. It's not the same percentage. An experimental drug is administered to 100 people with the number of individuals responding favorably recorded. So they're going to ask them, do you like it or not like it? So this time they're going to either say yes, they like it, or no, they don't like it. So this time, finally, it's yes or no. We have 100 of them, so we know the n. The same percentage, it doesn't. Once we figure out how many say yes and how many say no. So this one answer is yes. It doesn't ask. I'm thinking of something else here for binomial experiment. Binomial experiment simply means they have to say yes or no, and we have to know how many there are. So here's the n. They're asked whether or not they believe Congress should reform Social Security. People are going to say yes or no. So we know how many. They say yes or no. So this is a yes. 3 cards are selected without replacement. The number of aces are recorded. Okay, we have 3 cards. So that's n. So that's check. The first one is either yes or no and ace. The next one, yes or no and ace. The next one, yes or no and ace. So it's a yes or no scenario. Again, this is yes. 3 cards are selected. The number of kings is recorded. See, now putting this, okay, the same percentage all the time. See, now if we go king, 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 they did not say we put them back. So the first king would be 4 out of 52. The next king, there would only be 3 out of 51. So this one is a no because it is not always the same percentage. Let me go back up here and check these for same percentages. See, I think we got to turn this one back to no because there's still not a percentage happening there, and there's still not a percentage happening there. It does have to, each chance has to always have the same chance of happening. So by putting these back, that would be a 4 out of 52, a 4 out of 52, and this could be a 4 out of 52 for yes. I think the only one that's a yes is probably E. Those are weird questions. Okay, let's see if we can apply them here. Claridex is medication whose purpose is to reduce the symptoms of allergies. In a clinical trial, 5% of all patients had a side effect of insomnia. So we have 5%, so there we go, 5% always have that. A random sample of 20, so there's N, is obtained and find the number of patients who experience insomnia recorded. Find the probability that exactly 3. So we want the probability of 3. Okay, so it is binomial because the 5% is everybody. We have 20 of them and we want 3. Okay. We have that in our distribution. Second distribution, it's binomial. PDF is the individual, CDF is the accumulation. So they only want one individual of 3s. So yours is a little bit different. You're going to say PDF 20, comma 05 for the percentage, comma 3. Mine asks it a little bit, it still wants the 20, but it asks it as a word. What's the percentage, 05, and how many do we want? 3. See, it pastes it in, it doesn't make you, it pastes it in binomial, 20, 05, 3 is 06%. Well, they put the whole thing, 0596. Okay, here we want 3 or fewer. So we want 3, we want 2, we want 1, or we want 0. We could just do it 4 times and add them all up. But that's what CDF is. If we do binomial CDF, 20, 05, 3, that finds this number down. It adds 3 down to 0. So it does this for us. So if we just go binomial distribution, binomial CDF, 20, 05, 3. See, there's the binomial CDF 20053. That's 984. Find the probability that between 1 and 4 inclusive. So this time they want 1 and 2 and 3 and 4. We could do the individuals and add them up. Or we could do the CDF from 4. So that'll get us all the way down to 0. But then we have to throw out 0. So we could do binomial CDF from 4 down and then subtract binomial PDF of just the 0. Okay, so see, CDF takes it all the way down. If they don't want the 0, we'll subtract the 0. So let's see, let me do the 4. Distribution, CDF, 20054 minus PDF. $20.05, just the 0. Oh, darn it. $20.05, just the 0. So see, I've got the, if you can see it all now, I'll just scroll it. See, I've got the CDF, blah, 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 minus the PDF of the 0. Grand total of 6389. Oh, there it is. They have that. Would it be unusual to find 4 or more patients with side effects? 4 or more. That's 4 plus 5 plus 6 all the way up to all of them, plus 20. Okay, so remember, we already did these down here. We did 3, 2, etc. We did that right here. So from this point down, had an answer of 9841. See, all of these were 9841. So these are whatever's left. So 1 minus 9841 is up here. Okay, so would it be unusual? Yes, unusual. Because only 1.59% would of the time it would happen. Okay, so here's 21, the exact same stuff, 5%. Okay, so it's the same data. Now we have 240 users. How many would we expect to experience insomnia? Okay, well, we have 240 users and 5% of them will get it. So 240 at 5%, 12. Would it be unusual to observe 20 patients experiencing, so to observe exactly 20. So they want the probability of just 20. That's PDF. So the binomial of PDF, when we have 240 people at 5%, exactly 20. So the binomial of 240 people at 5%, we want exactly 20. So it's the PDF of, oops, I put 250, it should be 240. So that's 0.0087, 0088 if we round it. So would it be unusual? Yes, unusual. Because only, so if I move the decimal twice, 0.88% would happen. Okay, number 22, we're coming down the home stretch here. The following are correlation coefficients for 3 pairs of data. Which pairs of data are mostly highly correlated? So 1 is perfect. That means the data goes in exactly a straight line. Positive 1 means it's got a positive slope. So positive 1 is perfect. It's like eat a lot, get fat. Eat a lot, get fat. It's a high correlation. Negative 1 means the same thing. It just means you get smaller. So negative 1 is also perfect. 0 is totally random. Like your shoe size versus your grade point average. The dots don't have any relationship at all. So 0 is bad as you can get. So the scale goes from negative 1 is perfect to 0 is random back to 1 is perfect. So perfect, random, perfect. So the closer to 1 you get, the closer you are. So like 0.8, negative 0.8, the negative means it's going down, and they're almost in a straight line. They're just not quite perfect. So the closer you get to 1, and so 0.5 means they're a little bit more scattered. See, it's more towards random, but they're still going up, but more scattered. So the most highly correlated is this one because it's almost perfect. That means those are going almost in a perfect straight line down. This is the worst one because it's almost 0.